Welcome back to Nature in Code. We're in chapter 3 and we are in the process of developing an intuition for genetic drift and, even more excitingly, to implement it in code in JavaScript. So just to wrap up for what we've done before so far, in Hardy-Weinberg land, so to speak, from chapter 2, we noticed that the allele frequencies P and Q never change, so we don't have evolution, because evolution is defined as the change in allele frequencies in a population over time. That doesn't happen in the Hardy-Weinberg world. In the last video, we developed this intuition that if we make one change in the Hardy-Weinberg assumptions, if we in fact go from an infinite population size to a finite population size n, then we introduce something that we called random sampling. And that random sampling has dramatic effects on the allele frequencies. And we developed an example with a coin tossing application where we started with allele frequencies for A1 and A2 at equilibrium at 50%. And then within one generation, we were at A1 frequency of 65% and at a A2 frequency of 35%. So dramatic evolutionary change within a single generation. And the only difference from the Hardy-Weinberg world, where we would have no evolution, no change in the allele frequencies over time, was that we went from this infinite population size to a finite population size. And so what we would like to do now is we would like to implement this idea in code. So let's go over to our text editor. So this is the coin flipping example that we developed in earlier videos. And we're now going to develop code to implement genetic drift. And you'll notice that it's going to be quite similar in spirit. So let me open a new file. Let me in fact copy this code here, open a new document, paste this, and get rid of all the JavaScript here. And so now we can start from scratch with new code. So I'm going to start by defining again P, the variable that holds the A1 frequency. And I'm also going to now introduce a new variable that I'm going to call n, which is the population size, and I'm going to define it here to be a value 1000. And now I'm going to develop this function next generation. And you may recall from the Hardy-Weinberg videos that this function was very simple. It basically just calculated the genotype frequencies based on the allele frequencies. In this chapter, we actually don't care about the genotype frequencies. We just care about the allele frequencies first, because that's really where sort of the meat is, because again, evolution is defined as change in allele frequencies. So we really just want to see, does evolution happen now when we have genetic drift? And so as before, where we flipped the coin, we're now picking alleles, and I have to define how often I want to do that. And I need to do this, as we established in the last video, 2n times, because our population size is n, and we have diploid individuals, so we need 2n individuals in each generation. Now I'm going to define these two local variables here, A1 and A2, and those are just counters for the number of A1 or A2 alleles that I'm drawing here, that I'm picking from the gamete pool. And this is similar in spirit to the heads and tails variables in the earlier code. All right, so like before, now I'm going to implement here a loop of our I equals 0, and then I'm going to iterate here for however many draws of alleles we need to do. And of course, I have to be careful to increment the variable I here, otherwise I'll get an infinite loop. So I'm going to draw an allele, and I'm going to do this like before from the coin tossing example by basically calling math random, so by generating a random number between 0 and 1. And I can now say, okay, like before, if this is smaller or equal to 0.5, then before I was implementing the heads or the tails variable, here I'm going to now increment, excuse me, the a1 variable. And if that number should be larger than 0.5, then we say, okay, that means we picked an A2 allele, and so correspondingly I'm going to increment the A2 counter here. Now, we wrote this condition here before because we said we had a fair coin, and a fair coin comes up 50% heads and 50% tails. Now, our math random here is not necessarily a fair coin. It shouldn't be implemented as a fair coin, this line here. We want to draw alleles according to their frequencies, and those frequencies might change and might not be 0.5. So what I have to write here is P, because essentially I'm saying whenever this number is smaller than P, and P being the fraction of A1, then that means I've drawn an A1. So why does that work? Well, imagine P would be, say, 0.3. Well, in math random, we get a random number between 0 and 1, and each random number is equally likely to come up. So indeed, in 30% of the cases, this number will actually be smaller than 0.3. And so we can say, in this case, with 30% probability, or whatever P is, we'll pick an A1 allele. And so all I have to do now at the end, after I've done this 2n times, is to recalculate P. So what do I have now as P? Well, just the number of A1 alleles that I picked from the gamete pool divided by the number of alleles that we have, which is draws, which is 2n. All right, so this should work. So this is the function that calculates the new allele frequencies in the next generation. So what I would like to do now is I would simply like to call this function a number of times. So I'm just going to implement another loop here. I is smaller than, say, 1,000. Say we do this 1,000 times. And of course I have to increment I here to avoid infinite loops. Then I'm going to call this function that we just defined next generation. Actually, let me put this in a variable here. Let me define a variable generations up here and set this to 1,000. And now, rather than hard code this here in the loop, I'm just going to use this variable. Okay, so this should work. However, we wouldn't see whether it works or not because we're not showing anything. We're not printing any values into the console. So let's go ahead and do that. Console log. So first I need to know which generation we're at. And I'm going to use string concatenation, and I here can serve as our generation counter because it's increased by 1 at every generation. And then I want to print P, and we might as well print 1 minus P, which is the frequency of the A2 allele. Okay, so let's save this. It's a new file, so let me save this here in chapter 3 as drift.html. Okay, so let's go over to the browser. Here's still our heads. Google Coin Flipper. Let me open this new file. Open file, chapter 3 drift, here it is. And let's take a look at the JavaScript console, view developer JavaScript console. And here it is, and you can see all these values here that came up in this particular case. And this looks a little ugly. This is, of course, our friend, the rounding error. But we actually have already developed a function that could take care of that. So let's go ahead and reuse that here. Let me open the file where we defined this function. This was in chapter 2 in the file, my first document. Here it is, this function round number that takes 2 parameters. So let me copy this over to the drift file here. And now this is where the rounding occurs. So rather than saying print P, I'm going to say print P after it's been processed by this round number function, which takes two parameters, P, the value that should be rounded, and the number of decimals of precisions. And I'm going to use 4 here. And same over here, instead of 1 minus P, we'll print round number 1 minus P and 4. So save it, reload it, and now this looks much nicer. So if you look at these allele frequencies, you can see they fluctuate widely, right? I mean, we start with 0.5, and then here the A1 allele goes down in frequency to 30% or so, but then comes back up, goes back down again here. Let's see what happens here. Oh, goes down to 10-15% or so. Even it goes down further to 6% here in generation 850 or so, but then makes a comeback, comes back up to 15-16% or so, goes down a little bit again. But in any case, you can see that the frequencies change quite a bit. So let me reload this again. And here's something that's really interesting. So something happens here in this simulation at the very end. The A1 allele is actually lost from the population, and correspondingly the A2 allele has gone to fixation. It's now 100% of all alleles. That's really interesting. Let's reload this again. So it didn't happen here, but lots of fluctuation over time. Same here. I'm just reloading a bunch of times. Okay, here again we have this phenomenon where around generation 900 in this case, one of the alleles, A1 here in this case, went to fixation, A2 was lost. Reload this again a couple of times. Let's see if we get this, if we can recreate this phenomenon again. Here. And here that actually happens quite early on at around generation 670. The A2 allele goes to fixation and the A1 allele is lost. And what you'll notice is that once that's happened, that's it. No more evolution, no more change in allele frequencies. Why is that? Well, there is no process that could bring the A1 allele back here because this population will not produce any A1 gametes anymore, and so there's no A1 alleles to be picked. So this loss of genetic variation is final in this simulation, and that's really one of the key consequences actually of genetic drift, is that it reduces genetic variation. And in the next chapters, we develop more intuition for what exactly happens, why this happens, how often it happens, and in particular also how quickly it happens. And another thing that we'll do is we will introduce the concept of visualization, because going here through these allele frequencies, hundreds of lines of output, is a little cumbersome, and we should build on JavaScript's and the browser's strength to visualize things, and we'll do that in the next video. So I'll see you in the next lecture.